For the last 2 episodes, we've been dropping a ball into a valley and watching it find its way to the bottom. It worked, but I lied to you. And today, I have to come clean. Our ball isn't a ball, it's a ghost. No mass, no inertia, no memory. Every single step, it looks down at its feet, teleports a little, and then forgets everything that just happened. A real ball doesn't behave like that. And it turns out that the one way our ball is unlike a real ball is exactly what makes gradient descent painfully, agonizingly slow. Same valley. Same gradients, exactly the same gradients. The only thing that changed is what the ball does with them. One line of code. On a toy valley, that's 180 steps versus 23. On a real model, a week of GPU time versus a day. That one line is the difference between a lab that ships and a lab that runs out of money. Its name is momentum. And the story starts in the Soviet Union in 1964. 48 years before AlexNet, before anyone had a reason to care. Boris Teodorovich Polyak, Soviet mathematician. He did not care about cats. He did not care about ImageNet. That didn't exist. He cared about one clean question. Why are iterative methods so damn slow? His paper was called Some Methods of Speeding Up the Convergence of Iteration Methods. It ran in 1964 in USSR Computational Mathematics and Mathematical Physics. And here's the part I love. His idea didn't come from mathematics. It came from physics. He modeled the optimization problem as that. A heavy object rolling in a bowl with friction. Not an update rule. Newton's equations of motion. He called it the heavy ball method. That name says everything you need to know. What gradient descent was missing was mass at m times x, 2 dots, plus mu times x, 1 dot, plus the gradient of f of x, equals 0, mass, friction, slope. That's not a machine learning formula. That's a physics problem from a high school textbook. 19 years later, another Soviet mathematician, Yuri Nesterov, did something even bolder. But to understand what he did, you first have to know that the finish line had already been drawn, Nemborovsky and Yudin. Their work established a lower bound. For smooth convex problems, no method that only ever looks at first derivatives can beat big O of 1 over k squared. Ever. Not with more cleverness, not with more compute. It's a wall built into the mathematics itself. So the field knew exactly where the finish line was. Nobody could reach it. For years, the best anyone had was this. Gradient descent on smooth convex problems achieves big O of 1 over k. And then Nesterov walked up and put his hand on the wall. Nesterov, 1983, achieves big O of 1 over k squared. His 1983 paper, a method of solving a convex programming problem with convergence rate O of 1 over k squared. He didn't find a fast method. He found the fastest one that can exist. The problem closed, and then nothing happened. For nearly 30 years, Nesterov acceleration lived in convex optimization conferences. It got taught to math PhD students, and it was treated as a theoretical ornament. Why? Go back and listen to that guarantee again. It was proven for convex functions. Convex means one valley, one bottom. Drop the ball anywhere, it ends up in the same place. A neural network is about as convex as a mountain range. Nesterov's proof said nothing about that. So the machine learning world looked at the most beautiful result in convex optimization and said, lovely, not for me then, 2013. ICML, Ilya Sutskever, James Martins, George Dahl and Jeffrey Hinton publish on the importance of initialization and momentum in deep learning. Set the scene because the drama matters. At that moment, the field believed that training deep networks and recurrent networks required expensive second-order machinery. Hessian-free optimization, an entire research program. This group showed good initialization, plus momentum tuned properly, with beta pushed as high as 0.99, was enough, a 50-year-old idea. 2 lines of code. It beat an entire research program. They also did something quietly essential. They rewrote Nesterov's formula into a form you could actually use in deep learning. We'll get to that. An idea borrowed from high school physics. Asleep for 30 years. Woke up and became the thing running inside every AI model you touch today. But why? Why does giving a ball mass matter this much? Back to the valley. This is the soul of the episode. No equations here. Names only. Not one thing to solve. Let's put our GD ball next to a real ball on the same slope. Listen to that middle row again, because it's the whole lesson of this episode. In gradient descent, the gradient is the steering wheel. In momentum, the gradient is the gas pedal. You're not steering the ball anymore. You're pushing it. 2 new rows. That's everything this episode adds. 2 rows. And they change the behavior completely. One warning, because this trips people up. You might expect 2 knobs here, one for the ball's mass, one for friction. There aren't 2. There's 1. Mass and friction aren't separate settings in this world. They're the same dial, seen from opposite ends. Turn beta up and you get a heavy ball in thin air. It remembers a long way back. It's hard to stop. Turn beta down and you get a light ball in syrup. It forgets almost instantly, and it barely differs from the ghost we've been using for 2 episodes, at the value everyone actually uses. A push from any given step fades to nothing after roughly 10 steps. 10 steps of memory. That's the entire upgrade. Hold on to that number. In the next part, we'll see exactly where it comes from. This is the most important minute of the episode. Deliver it slowly. Picture yourself rolling down a narrow trough. Steep walls on both sides. And down the length of it, a gentle grade toward the far end. Your ball is getting hit by 2 kinds of force. Force 1, sideways. Slam from the left wall, slam from the right wall. Left, right, left. It flips sign constantly, force 2. Forward, along the trough. Much weaker, but always the same direction. Now, what happens when the ball has memory? When it adds these up? The force that keeps flipping sign cancels itself out. Add it, subtract it, add it, subtract it. You're left with almost nothing. The force that always points the same way, stacks. Adds, adds, adds. It grows and grows and grows. Momentum is not smarter than gradient descent. It doesn't know one extra thing about your function. It does exactly one stupid, almost comically simple thing. It adds things up. And that one stupid act automatically kills whatever is inconsistent and automatically amplifies whatever is consistent. So that's the bargain. And I want to be honest about both halves of it. Momentum doesn't avoid the oscillation. For the first few steps, it makes the oscillation worse. You saw it at the top of this episode, the ball slamming the wall harder than the ghost ever did. It just refuses to keep paying for that oscillation forever, while it happily keeps collecting on the trend. Paid once. Collect forever. That's the deal. Hold on to that word. Overshoot. It's going to come back at the end of this episode, and it will not be so easy to forgive. One last thing before the math. What we just watched has a name in signal processing. It's a low-pass filter. Momentum filters your gradients. It blocks the high frequencies, the oscillation. It passes the low frequencies, the trend. Now let's write that down as math. I promise, it's one line. Theta at step t plus 1 equals theta at step t minus alpha times g at step t. Write it like a sentence. New position equals old position minus a small step along the slope. Notice, g at step t goes straight into the position, nothing in between. That's a ball with no mass d phi at step t equals beta times v at step t minus 1 plus g at step t. Then, theta at step t plus 1 equals theta at step t minus alpha times v at step t. Write both lines as sentences. Slowly, line 1. New velocity equals some of the old velocity plus the push from the current slope. Line 2. We step along the velocity, not along the slope. Compared to the old formula, the only thing added is beta times v at step t minus 1. Memory, that's all of momentum. Polyak, 1964. 2 lines, and notice, the old formula didn't get replaced. It's still in there. Turn beta down to 0 and the ghost comes back. Episode 1 is just momentum with amnesia. The line v at step t equals beta times v at step t minus 1 plus g at step t looks mysterious. So let's unroll it backwards. Substitute v at step t minus 1 with its own definition. Then do it again to v at step t equals g at step t plus beta times g at step t minus 1 plus beta squared times g at t minus 2 plus beta cubed times g at step t minus 3, and so on. The sum, from I equals 0 to t, of beta to the power I times g at step t minus I. There it is. No magic anywhere dv is just a sum of past gradients with exponentially decaying weights. Last step's gradient times 0.9, the one before times 0.81. The one before that, 0.729 more, doesn't vanish. It fades, and that has a name, an exponential moving average. Memory fades, but how far back does it reach? There's a number that answers that. Suppose the ball rolls on a constant slope. The gradient is always g. Where does velocity settle? V infinity equals g plus beta times g plus beta squared times g, and so on, which equals g over 1 minus beta, an infinite geometric series. With beta equals 0.9, v infinity equals 10 times g, and before we read the number, feel it. A real ball on a real slope doesn't accelerate forever. Friction eats the gain, and it settles at a terminal velocity. That's exactly what this is. Beta is the friction. 1 minus beta is the drag. Our ball has a terminal velocity, and the formula just told us what it is. Now read it again. On a constant slope, momentum doesn't move a little faster than gradient descent. It moves 10 times faster. At beta equals 0.99, Sutskever's number 100 times faster. And there are 2 ways to read that same number. Hold both in your head. First, memory length. Beta equals 0. 9 means the ball remembers roughly the last 10 steps. Second, effective learning rate. Once the ball is up to speed, momentum has quietly multiplied your learning rate by 10. Hold on to that second reading. Because it means alpha and beta are not independent. When you raise momentum from 0.9 to 0.99, you have just silently multiplied your learning rate by 10. A lot of people turn momentum on, watch the loss explode, and blame momentum. No, You just multiplied your learning rate by 10 without noticing. We're coming back to this. It is not a gotcha. It is a structural crack. Step 3. Gradient descent is still up at 5. Momentum is at 0.62. It's there. It's basically done. Now watch step 4. It shot past, and it kept going. By step 6, it's further from the target than gradient descent has ever been, and it's on the wrong side. So let me be honest with you, because this is the part most explanations quietly skip. On this valley, momentum loses, badly. It does converge eventually. It spirals in, but on a clean round bowl, mass buys you nothing and costs you everything. Which should bother you? We opened this episode with 23 versus 180. So, where did that come from? A round bowl is not where momentum earns its living. It earns it in a ravine. A valley that's steep across and nearly flat along. And you cannot build a ravine with one variable. You need two. That's the next part. But before we go, look at step 4 one more time. It shoots past the target. A real ball does that. Remember this moment. Nesterov was born right here. F of x equals x squared. Here's something they don't tell you. On a single variable parabola with a well-chosen step size, plane gradient descent lands at the bottom in one step. Momentum doesn't help. At all. That's not a disappointment. That's the clue. Momentum isn't a trick for going downhill faster. Going downhill was never the problem. Momentum is a cure for a disease that doesn't exist yet. Because in one dimension, there's only one direction, and one direction can't disagree with itself. Give it a second direction, and the disease appears instantly. F of x, y, equals x squared, plus 100 times y squared. Two directions, and they disagree. Take the second derivatives, the curvature in each direction. Along x, 2. Along y, 200. Those are the eigenvalues of the Hessian, and for a trough this simple, you can read them straight off the equation. One direction is 100 times more curved than the other. That ratio, steepest curvature over flattest curvature, is called the condition number, written kappa. Here, kappa equals 100. Remember that letter. Kappa is the villain of this entire episode. And now look at the picture again, because there's something sneaky in it. Kappa is 100, but the ellipse you're looking at isn't stretched 100 to 1. It's stretched 10 to 1. 10, the square root of 100. That's not a rounding error. Your eye sees the square root of kappa. Your optimizer suffers kappa. The pain is the square of the ugliness. Hold onto that gap between kappa and the square root of kappa. In part 6, it's going to turn out to be worth everything. Now, your neural network doesn't have 2 parameters. It has 100 million. Same loop you've known since episode 1. Forward pass, loss, gradient, step. But the surface that loop is walking on now has 100 million dimensions. And I'm going to be honest with you. Don't try to picture it. You can't. I can't. Hinton can't. But the machinery survives the jump. There's still curvature in every direction. There are still eigenvalues, 100 million of them. There's still a worst to best ratio. There's still a kappa. That's a real measured spectrum from a real network. Look at that tail, and look at the pileup at 0, because I owe you a correction. I said largest over smallest. But in a real network, the smallest eigenvalues aren't small. They're 0. Some of them are negative. The surface curves downward in those directions. Divide by that and kappa doesn't blow up. It stops meaning anything at all. So the honest version is this. Kappa isn't one number stamped on your network. It's local, a property of wherever the ball happens to be standing right now. Take one step, and the whole spectrum shifts underneath it, which is exactly the fog. Our ball has never been able to see the valley. Now I'm telling you, the valley doesn't even hold still. Measure kappa locally along a real training run. Largest curvature over the smallest positive one. And it doesn't come out at 100. It's routinely 10 to the 4th, 10 to the 6th, sometimes worse, and it changes while you watch. In theory, you just iterate and you're done. But when kappa is a million, and it's a different million every step, what does just iterate actually mean? The trouble starts. This is the parent problem. The other three are its children's ask. What should the learning rate alpha be? Upper bound. Alpha has to be small enough not to explode along the steepest direction. The math is explicit. Alpha has to be less than 2 over L, where L is the largest eigenvalue. Lower bound. But your progress toward the goal is governed by the flattest direction. The smallest eigenvalue, mu. See the trap? You have exactly one knob, alpha, and it has to serve 100 million directions with different curvatures. The steepest direction sets the ceiling. The flattest direction sets your speed, and the ratio between those two is exactly kappa, the result. GD needs roughly kappa steps to make progress. Kappa equals 10,000? Get comfortable. The GD ball in a stretched trough. It isn't wrong. The gradient genuinely does point down the steepest way. But the locally steep direction is not the direction to the goal. In a stretched trough, the gradient points almost perpendicular to where you need to go. And remember what stretched means at real scale. Our trough is drawn 10 to 1 so you can see it. A real loss surface runs kappa in the thousands. Take this trough and stretch it 1,000 times longer. People say, gradient descent goes the wrong way. That's false. Keep the step size under that ceiling we just found, and gradient descent never goes the wrong way. Every single step reduces the loss. The problem isn't that it's wrong. The problem is that it's short-sighted. It optimizes for the next step instead of the journey. It is a perfect, greedy, short-term thinker. And that short-term perfection is precisely what kills it long-term. Small gradient, small step, crawl. And for a massless ball, gradient approximately 0 means frozen forever. Gop to episode 2. In high dimensions, saddle points outnumber local minima exponentially. Around a saddle, the gradient is tiny. Our ball just sits there. Last episode we saw it. Mini batching makes the gradient shake like a drunk hand. The GD ball has no memory, so it believes every single tremor. It performs a random walk superimposed on the right direction. 4 problems. But they are not equals. So before we fix anything, rank them honestly. Our enemy is not noise. It is not local minima. Our enemy is kappa, the geometry of the valley itself. Noise is a tax. Saddles are a delay. Kappa is the thing that decides whether you finish this year. Now here's the miracle. Polyak's one line patches all 4. Though one of them, as you'll see, it patches for a reason nobody saw coming. Not 4 solutions. 1. V at step t plus 1 equals beta times v at step t plus g at step t. theta at step t plus 1 equals theta at step t minus alpha times v at step t plus 1. Read the top line as a sentence. Keep most of where I was already going, that's beta times v at step t, and add where the ground is pushing me now. And then the bottom line, step along that, not along the raw gradient. The gradient stopped being a command. It became some advice, same formula I showed you in part 3, but now it means something. Now, look at rows 3 and 4 together and notice something uncomfortable. Row 4 says, momentum filters out the noise. But the whole lesson of episode 2 was that the noise is what kicks you off the saddle in the first place. So momentum coasts through saddles, while quietly muting the one thing that used to rescue you from them. It gives with one hand and takes with the other. Hold that thought. We come back to it in part 8, and it doesn't have a happy ending. This is the most expensive number in the episode. On a strongly convex quadratic with condition number kappa, gradient descent needs order kappa steps. Momentum needs order square root of kappa. That sounds dry. So plug numbers in. Forget absolute step counts. Those depend on how much accuracy you demand. Watch the ratio. Kappa equals 100. Momentum gets there in 1/10 the iterations. 10 times faster. Kappa equals 10,000 100th. 100 times faster. Kappa equals 10 to the 6th 1,000th. Same accuracy, same valley, one line of code. And notice what that means. The worse your valley is, the harder momentum wins. This is not a 5% tweak. This is a change in order of magnitude. That is why an idea from 1964 is still sitting inside every optimizer you use. But remember the numerical example from part 3? The ball overshot. And now we can say exactly why. The ball is blind. It computes the gradient where it's standing and then rolls away. But by the time it lands, the landscape has changed. It is braking on stale information. It's a driver watching only the patch of road directly under the tires. By the time you see the curve, you're in it. Nesterov asked an almost childish question. What if it looked a little further ahead? Momentum, v at step t plus 1, equals beta times v at step t, plus the gradient of f at theta t, measured right where the ball is standing now. Nesterov v at step t plus 1 equals beta times v at step t, plus the gradient of f at theta t plus beta times v at step t, measured where the ball is about to be. The difference is 4 characters. Theta t became theta t plus beta vt. Read it as a sentence. My inertia is going to throw me over there anyway. So instead of measuring the slope here, let me measure the slope over there, and then decide. Polyak's ball rolls, then looks. Nestorov's ball looks, then rolls. What is Nestorov's correction, really? Take the difference between the two gradients. The gradient of f at theta t plus beta vt minus the gradient of f at theta t is approximately equal to the Hessian of f at theta t times beta times vt. Look at that right-hand side. Look hard. That is the Hessian times a vector. That is second-order information. That is information about curvature, which means Nesterov is quietly stealing a little bit of curvature information. The thing that in principle only second-order methods have, without ever computing a Hessian, without paying the order n² memory bill. It gets it by measuring the slope somewhere slightly different. This is the intuition for why Nesterov is more stable than heavy ball, and for why its convergence rate can reach the theoretical lower bound for this class of methods. It isn't faster because it's more reckless. It's faster because it knows more. The 1983 form uses two sequences of points, theta t and yt, along with a sequence of coefficients beta t that changes every step, not a constant 0.9 generated by lambda at step t plus 1 equals 1 plus the square root of 1 plus 4 times lambda t squared, all divided by 2. It's ugly, and it assumes convexity. Bengio and colleagues in 2012, then Sutskever et al. In 2013, rewrote it into a single sequence form with a constant beta, which is exactly the formula I just showed you. The 2013 paper is the one PyTorch docs still point at today. That rewrite is the reason you can type Nesterov equals true, a bridge from pure convex analysis in 1983 to a Boolean flag in a library. That's what those papers bought us. Look at the tree. Two families. They grew up without knowing about each other. One asking, which way do I step? The other asking, how big is the step? Neither one ever replaced the other. Momentum was never replaced. It got married. When you type torch.optim.atom, the default beta 1 equals 0.9. That is Polyak's beta. Same number, same job. 60 years later, still deciding how much of the past your ball is allowed to remember. And it is sitting inside the optimizer that trains essentially every large language model on this planet. From here on, for every application, ask yourself 3 questions. 1. What is the error measuring? 2. What is being adjusted? 3. What's the actual scale? You'll see it's always one ball, one trough. Why this one gets the most time. It is the one place where SGD plus momentum has still not been displaced. It is the strongest living evidence for this episode's thesis. What's the error measuring? Cross entropy. How confidently the model bet this image was a cat, and how much it gets fined for betting wrong. What's being adjusted? The weights of the convolutional filters. ResNet 50, roughly 25 million parameters. What's the scale? ImageNet, 1.28 million images. About 90 epochs at batch 256, around 450,000 update steps. Every step, the ball nudges forward in a 25 million dimensional space. The history. AlexNet 2012, the paper that won ImageNet and launched the deep learning era, trained with SGD and momentum equals 0.9. ResNet 2015, momentum equals 0.9. And here's the expensive detail. In 2026, the standard ResNet and CNN training recipes still run SGD with momentum 0.9. Now, be precise about what I am not saying. Vision transformers use AdamW. Nearly everything with attention in it uses AdamW. Momentum did not win everywhere. But on convolutional networks, the gap never cleanly closed. Adam has existed since 2014. It's more modern, it's smarter. And on CNNs, if you're willing to pay for the tuning, plain SGD with momentum still generalizes better, and people are still arguing about why. That's the thesis of this episode in one sentence. Momentum didn't survive by being clever. It survived by being right about something nobody has fully explained yet. Practitioner tricks. And notice they all trace back to things we've already covered. Learning rate warm-up. Because momentum multiplies your effective alpha by 10, and a cold start with a 10 times alpha explodes. Cosine decay. Gradient clipping. 62 years after Polyak. One number, 0.9. Still there. What's the error measuring? Cross entropy on the next token, how badly the model bet on the next word, what's being adjusted. Hundreds of billions of parameters. What's the scale? Trillions of tokens. Tens of thousands of GPUs. Months of wall clock time. The optimizer here is AdamW, not pure momentum. But open AdamW up and look at the first line. Beta 1 equals 0.9. Almost Polyak's line. Almost. Watch the one difference. It's the whole reason Adam feels different to use. Polyak's velocity is a running sum of gradients. Adam's is a running average. That little 1 minus beta 1, that's 0.1, is doing one job, dividing by 10. 10. Where have we seen 10 before? That's the gain from earlier. Polyak's heavy ball secretly multiplies your step size by 1 over 1 minus beta, by 10, which is exactly why you needed warm-up to survive the first 100 steps. Adam just divides it back out, same skeleton. Gain removed, because Adam controls step size somewhere else. In the second moment, so no, AdamW didn't replace momentum. AdamW is momentum, with a volume knob bolted on. Polyak's line is still in there 62 years later, running on tens of thousands of GPUs, doing exactly what it did on paper in 1964. And at this scale, the gradient is brutally noisy. Your batch is microscopic relative to the dataset. So momentum's noise filtering isn't a nice to have. It's a survival requirement. What's the error measuring? Negative expected reward. You played badly, you get fined. What's being adjusted? The policy network's weights. What's the scale? Billions of simulated frames. Why momentum matters especially here. RL gradients are far noisier than supervised learning, not by a little. Rewards are sparse. You make 1,000 decisions and find out at the end whether you won. Trajectories are random. The signal is buried. Without a low-pass filter averaging over that mess, you aren't training slowly. You're not training at all. And here's my favorite loop-closer: momentum was not born for AI. Polyak wrote it for iterative methods, solving systems of equations. There were no neural networks. There was no reason for him to care about cats. And it turns out he wasn't even alone. Look at conjugate gradient. Hestines and Stiefel, 1952, 12 years before Polyak. Open it up, and there's a term that adds a fraction of your last direction to your next one. That's inertia. They just didn't call it that. The same idea, under other names, has been running inside scientific computing for 70 years. Aerodynamic simulation, weather forecasting, structural analysis of bridges. Every time somebody solves a system with 1 million unknowns, inertia is in there. The bridge you drove over this morning was very probably designed by a heavy ball rolling downhill through fog. Go back to the ball at the top of this episode, 180 steps versus 23. Now you know where those numbers came from. That trough had a condition number kappa approximately equal to 60. Gradient descent pays kappa. Momentum pays the square root of kappa, the square root. That's the whole episode. That's the entire difference between a ghost and a ball. And you know that a Soviet mathematician in 1964, working on a problem that had nothing to do with cats, called it the heavy ball. So that's it? Momentum wins. Clean sweep? No. Remember I said Polyak pays the square root of kappa. I never said he can always prove it. And the next part is my favorite part. This is where credibility is earned. Do not cut this. Do not soften it. In part 6, we patched 4 holes. But there's a different category of limit. Not a bug to be fixed. but an inherent price, no matter how well you tune beta, no matter whether you use Nesterov instead of heavy ball. These stay. These are boundaries, not bugs. Every bit of that square root of kappa magic in part 6 was proven for exact gradients. But you don't have exact gradients. You have mini batches. You have noisy gradients. And here's the uncomfortable truth. Kidambi et al., 2018. The paper is titled, "With No Diplomacy Whatsoever, on the Insufficiency of Existing Momentum Schemes for Stochastic Optimization." The finding, in the stochastic setting, heavy ball and Nesterov, the two schemes sitting in your optimizer right now, do not deliver acceleration over plain SGD. Be precise about what that does and doesn't say. It does not say acceleration is impossible under noise. In fact, and this is the twist, the same authors, in the same paper, build an algorithm that does accelerate, ASGD, so acceleration survives the noise. Your formula doesn't. Why? Split your error in two. There's a bias term. How far you still are from the target, pure geometry, governed by kappa. And there's a variance term, the jitter your sampling injects, governed by sigma squared and your batch size. Acceleration only ever touches the bias half. The variance half is set by statistics, and statistically it's already optimal. You can perfect the geometry, and that half is still sitting there, untouched, waiting. Back to the metaphor. Inertia helps the ball pick a clever path through the trough. But if the trough itself is shaking, if the ground under it is randomly juddering, then being clever about your path stops meaning much. You cannot roll more precisely than the precision of the ground you're rolling on. And no beta you type in will steady the ground. So why does everyone still turn momentum on? Because in practice, it works beautifully. It filters noise. It coasts through plateaus. It boosts your effective alpha. It's just that it doesn't work for the reason Nesterov's 1983 paper says. The convex acceleration theory handed us the formula. But the things that make it useful in deep learning are different mechanisms entirely. We are using the right tool for slightly the wrong reasons. And the field is fairly comfortable with that. De Volder, Glinier, and Nesterov, 2014. And note that Nesterov himself is a co-author on this one. First-order methods of smooth convex optimization with inexact oracle. The result is counterintuitive, and it's gem number 3. If your gradients carry a small error delta, plain gradient descent generally does not accumulate that error. Accelerated methods do. The error compounds with the number of steps. Read that again. The very thing that makes it fast is the thing that makes it fragile. Momentum accumulates gradients. That's the strength. It accumulates signal. That's also the weakness. It accumulates systematic error too. There is no free lunch. Speed and robustness are two ends of the same lever, and that lever is called beta. Here's a fact that shocks people. With Nesterov, the loss is allowed to go up on some steps. Your loss curve will have ripples. That is not a bug. That is what the paper permits. Can you force it to always decrease? Yes. And then you lose the acceleration. The oscillation is the price of speed, not a defect in the design. There's a mitigation, adaptive restart, O'Donoghue and Candace, 2015. Whenever the loss ticks up, reset V to 0. But that's managing the price, not abolishing it. Metaphor. The ball has to climb a little way up the far wall to build the speed that carries it deeper. You cannot simultaneously demand that it be fast and forbid it from ever going up. Those are contradictory requirements, gopob to the cold open. Remember the very first thing our momentum ball did? Back at minute 1? It overshot. It looked worse than the ghost. You've now watched 35 minutes of video to learn that this was never a rough edge in the animation. It was the mechanism. Lessard, Recht and Packard, 2016, constructed a counter-example, a smooth, strongly convex function on which Polyak's heavy ball fails to converge. It falls into its Weissel and stays there forever. Honest footnote. Their function is piecewise quadratic. It has a Lipschitz gradient, and it's strongly convex. But it isn't twice continuously differentiable, which, if anything, makes it worse. You barely have to step off the quadratic to lose the guarantee. And here's the bitter part. Polyak's famous square root of kappa analysis is a local analysis for quadratics. Step outside quadratics and the guarantee evaporates. Nesterov, by contrast, does have a global guarantee for convex functions. That's why theorists prefer it, even though empirically the two are usually neck and neck. We used heavy ball for 52 years. In 2016, somebody finally proved it can fail spectacularly. This field runs ahead of its theory more than you'd think. Nesterov touches the Nemirovsky-Yudin lower bound. That is not a record waiting to be broken. That is a theorem. Want to go faster? Then you are required to pay for more information. Second derivatives, Newton, quasi-Newton, or exploitable structure in your specific problem. With gradients alone, you are done. There is no more road. Honest footnote. That lower bound applies while the step count is small relative to the dimension. But with 100 million dimensions, yes, you are always in that regime, metaphor. Our ball has exactly 1 sense. It can feel the slope under its feet. That's it. Nesterov is the best any creature with only that 1 sense can ever do. Polyak's 1964 idea, pushed to the literal edge of what the information allows. To go faster, you don't need a cleverer ball. You need a ball that can feel the curvature of the ground, not just its tilt. And that ball costs more than anyone at this scale is willing to pay. Back to the landmine from earlier. The effective alpha is approximately alpha over 1 minus beta. Alpha and beta are not two independent hyperparameters. Turning one is unknowingly turning the other. The practical upshot. Momentum is not an on-off flag. Turning it on redefines your entire learning rate schedule, metaphor. You thought you had a throttle and a separate flywheel. You have one throttle, painted to look like two. Every time you've reached for beta, thinking you were adjusting the ball's memory, you were also, quietly, kicking it harder. Look back at all 6 limits. There's a single thread running through every one of them. Momentum wins because it accumulates the past. And every one of its limits comes from accumulating the past. It accumulates signal, that's the power. It accumulates error. It accumulates speed until it overshoots. It accumulates learning rate behind your back. There aren't 2 mechanisms here. There's one mechanism, viewed from 2 sides. Momentum's strength and momentum's weakness are the same line of code. Momentum is this. Don't follow the slope. Follow the average of the recent slopes. That's it. One line. And here's the paradox I want you to walk away with. Momentum's acceleration was proven for convex functions. You use it on non-convex ones. It was proven for exact gradients. you use it with noisy ones. The guarantee you are leaning on does not cover the situation you are standing in. It isn't that the theory is silent. It's that the theory is talking about a different world. It works anyway. On every model, we are using a tool that performs better than its guarantees license, for reasons nobody has fully written down. That's not embarrassing. That's how science usually goes. Experiment runs first, theory follows, and the gap between them is where research lives. There's something lovely buried in this. Polyak did not invent inertia. Inertia was already there, in every ball rolling down every hill, since long before there were people to watch. He simply noticed that our algorithm had accidentally thrown it away. And he picked it back up. 60 years of optimization. And one of the largest jumps in the whole run wasn't adding something new. It was stopping pretending the ball had no mass. But there's a problem nobody has touched yet. Remember, one knob alpha, 100 million directions with different curvatures? Momentum didn't solve that. It sidestepped it by accumulating. The real question is, why should every parameter share one learning rate? Why should the parameter that sees data every single step and the parameter that sees data once in 1,000 steps be forced to take the same size stride? Next episode, AdaGrad, RMS Prop, and Adam. What happens when every parameter gets its own learning rate? And we'll see that Adam is really just today's inertia, plus a self-adjusting step size, bolted together. The beta you learned today walks straight into it. Under a new name, doing the same job, with exactly one character added. And that one character quietly disarms the trap you're about to walk into in 60 seconds. Keep it in mind. Before the next episode, do this for me. It takes 5 minutes and it will teach you more than this video did. Take any small network. Run it 3 times. Momentum equals 0. Momentum equals 0.9. Momentum equals 0.99. But don't just watch the loss. At beta equals 0.99, you just multiplied your effective learning rate by 100. So run a 4th time. Momentum equals 0.99 and divide your learning rate by 100. Now put all 4 on one axis. And look at run 4. It doesn't look like run 3. It looks like run 1. The run with no momentum at all. You cranked the inertia to the maximum, and the curve came back to where it started. So then, what did momentum actually buy you? The answer is in the first 50 steps, where run 4 doesn't match run 1. Go find it. Zoom in on it. If you can explain that gap, what lives in it, and why it's the only part of momentum that isn't just a learning rate wearing a disguise. You understand this episode more deeply than most people who ship these optimizers every single day. See you next time.